All right, let's look at example 2. So here we have this matrix A, which might look familiar to you because it was the same one from the warm-up exercise. And we have that A can be diagonalized using P and D here, where P is this matrix that has columns B1 and B2 that we can see are linearly independent from each other, which means that the two columns form a basis and P is invertible. So it makes sense to say P times D times P inverse. And D has this -2 and this -0.5 here. So we're going to show that B2 is an eigenvector of A two ways. The first way is just going to be by multiplying A times B2 directly. And we could just multiply it the regular way, like so. So yeah, the result of doing A times B2 is over here, this 1, 0.5, that is -1/2 of B2. So multiplying B2 by this matrix does the same thing as just scaling B2 by -1/2. So in other words, B2 is an eigenvector of A corresponding with eigenvalue -1/2. So that works to just multiply it directly that way. You could also say multiplying it directly could also mean just writing it as P times D times P inverse and doing that times B2. We're still just going to multiply it here. Well, what do we know about P inverse times B2? Well, we know that P inverse times P is the identity. We also know that we could think of that as a matrix whose two columns are each P inverse times the first column of P, and the second column is P inverse times the second column of P, and that should be the identity, right? So, in other words, P inverse times B2 should be equal to E2. And maybe we can write out what P and D are here as well. Another way to see that this P inverse times B2 is going to be equal to E2 is the same explanation we gave over here in exercise 2 warm-up. That works in general, but this is another way to see it. And from here, we know that we can just do 0, 1 times this D, and you're just going to get 1 times the second column. So we're really just doing B1, B2 times 0, -0.5. And that is just going to give you 0 times B1 minus 0.5 B2. So that's another way to see why this works. Now, let's also see what the diagonal coordinates theorem says about it. Here's the diagonal coordinates theorem. We're going to use, instead of y here, that'll be B2. And we know what the B coordinates of B2 is. Because what are the linear combinations of B1 and B2 that get you B2? Well, it's just 0 and 1, right? So in other words, the B coordinates of A times B2 are D times the B coordinates of B2, which is just D times E2, which is going to be 0, -0.5. And what does this mean? Well, it means AB2 is 0, B1 minus 0.5 B2, because those coordinates, 0 and -0.5, are the weights you need to multiply B1 and B2 to make the linear combination become out to be AB2. And that is, of course, just negative 0.5 b2. And so, yeah, this is also saying that b2 is an eigenvector of A corresponding with lambda equals negative 0.5. So this concept here works in general. We're kind of looking at it two ways. One, in terms of like just the straight up diagonalization, and also thinking about how multiplying anything by A is going to stretch out the B coordinates of that thing by the diagonal entries in D here. So that is an example of the diagonalization theorem working. Let's read it first, see how it relates to that example, and then we'll prove it. So this says a square matrix A is diagonalizable if and only if A has C linearly independent eigenvalues. And C is the number of rows and columns of A. And specifically, A is diagonalizable with P and D, like so, if and only if the columns of P are C different linearly independent eigenvectors of A, which correspond with eigenvalues in the diagonal of D in matching right to left order. And we saw that here, actually. We already knew that B1 was an eigenvector. Well, how did we know that? This 2, 0.5 is actually half of the V we had before. So if you multiply half of V by A, you're going to get half of AV. So this point here is going to be A times B1. So yeah, that's also going to be on the line through B1 and the origin. And so that is an eigenvector that corresponds with negative 2 as its eigenvalue. And we already showed that B2 is an eigenvector that corresponds with eigenvalue negative 0.5. So the second vector in P correspond with the second diagonal entry in D. That's what this says. So let's prove it. So we're actually going to prove the more specific version of this, but that also implies that the first sentence must be true as well. So first we're going to assume that A is diagonalizable with P and D, and then show that the columns of P are linearly independent eigenvectors of A. So let's write D as having diagonal entries D1 through DC, 0 everywhere else. We'll label P as B1 through BC, like so. And let's say that we're talking about column I of P. So we're going to say I is anything between 0 and C. Now the goal is to show that this column of P, let's say BI, is an eigenvector of A that corresponds with the matching diagonal of D. So in other words, we want to show that A times BI equals DI times BI. Now we can do this using the same trick from like the second way I did part A here, which is that since P inverse times P is the identity, the ith column of P inverse times P is going to be P inverse times BI, and the ith column of that must be equal to the ith column of the identity, which is EI. So we can use this with the fact that A is P dP inverse. So in other words, this A times BI is P dP inverse times BI. And the P inverse times BI part is equal to EI. And then we can multiply this out. Here's P, has these columns, and D looks like that, and we're multiplying that by EI. Well, we're just going to get the ith column of D here because we're doing 0 times all the other columns and then 1 times that column of D. So we get something with all zeros except for that ith diagonal entry here. And this is just, we're doing this linear combination where we do 0 times everything except that di times column I of P. We just get di times that column, which is what we're trying to show. We're trying to show that A times BI is equal to DI, which means that BI is an eigenvector of A corresponding with eigenvalue DI. So that's the only if part. Now we need to show the if part, that if the columns of P are C linearly independent eigenvectors of A, which correspond with the eigenvalues that are in the diagonal of D, then A is going to be equal to P dP inverse. So we're supposing we have these linearly independent eigenvectors that correspond with these eigenvalues, and we can put them in the matrices P and D. Like so. And we want to show that when we do P times D times P inverse, we get A. And the trick to doing this is we're going to say we have some I between 1 and C. And the goal is we want to show that no matter which I we're talking about, if we do A times EI, we're going to get the same thing as PD P inverse times that EI. Because A times each EI vector is just going to be that column of A. And likewise, we're getting the corresponding column of PDP inverse on the other side. And so if that's always equal, then we're saying each column of A, no matter what column we're talking about, is equal to the corresponding column of PDP inverse. So let's think about the B coordinates of EI. Let's say those coordinates are x1 through xc. In other words, we're saying that EI is the result of doing x1, b1, plus yada, 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 up through xc, bc. So if we want to see what A times E1 is, we can think of that as A times this version of E1 written in terms of the basis vectors. And then we have a distributive rule, an associative rule that says we can take out the scalars x1. And the reason we want to do this is because we know something special happens when we multiply A by its eigenvectors. We know that we get the corresponding eigenvalue scaling those eigenvectors as a result, like so. And from there, we can write this as a linear combination of the basis vectors. Well, it is a linear combination of the basis vectors, but I mean write it as a matrix times a vector, where those basis vectors are the columns of this thing, and we're multiplying them by the entries in this vector, just using regular old matrix vector multiplication. And if we take the diagonal matrix that has lambda 1 and then a bunch of zeros in it as the first column, and then same thing with all the other columns, make this a diagonal matrix that has those eigenvalues in it, and then multiply that by x1 through xc as a vector, then this matrix times vector product, is going to come out to be the same thing as this if you work it out. And lo and behold, what we have is P, that's the thing that has all the B's in it, times D times the B coordinates of EI. I said EI over here. It should be EI. I said E1 before. Whoops. Now, we know from before that the B coordinates of EI are the same thing as P inverse times EI. And again, maybe we can explain this part really quick, because we're saying EI is the result of doing P times the B coordinate vector of EI. If you were just to multiply both sides of this by P inverse, you just get that coordinate vector like so. So just making that substitution again. And that's what we were trying to show. We were trying to show that when we do A times EI, getting the ith column of A, that's the same thing as the ith column of PDP inverse. So there's a lot going on in this proof, kind of relating a lot of the things we've been hinting at for a while in 4.1 and 4.2 so far. So in the next few examples, which we'll look at in the next video, we'll think about how to apply it. I'll see you then.